Recording start agide madam. Matte start madbo.
Start madanalva session.
Okay.
Okay. Good evening, everyone. So today we'll be starting our first session regarding introduction to the quantum computing. So today our expertise is Vidya madam, and the session will be from 6:30 to 8 p.m. Before starting our session, let me introduce ma'am. Dr. C. Vidyaraj, Professor, CS&E and Dean Academic Affairs, the National Institute of Engineering, Mysore. Madam has completed B in CS&E, University of Mysore in 1989, MTech in Software Engineering in VTU in 2000, and PhD in Faculty of PhD in Computer and Information Science VTU in 2008 in Quantum Computing, and thesis titled Analysis of Fast Quantum Algorithms for Solution to Hard Problems on Quantum Computers under the guidance of Dr. M.S. Shivkumar, NIE CSE Research Center. Madam has 33 years of experience. She has 21 years of experience in research field. Positions held are Professor and Dean Academic Affairs to 2023 to till date, Professor in CS&D 2016 to till date, Professor, Principal and CEO from 2010 to 2016 on deputation to NIE, IT Professor and Head ISC in 2013, Professor and Head CSE 2008 to 2010, Assistant Professor CSE in 2000 to 2008, Lecturer as CSE during 1990 to 2000. Under MA/MS Research Supervision under VTU, Madam has guided already PhD students, 4 are awarded with PhD awards, and 2 PhD students are submitting their thesis, and 3 students are undergoing the PhD. And research areas are quantum computing, wireless sensor networks, body area networks, IoT protocols, cloud infrastructure, social IoT, smart infrastructure, machine learning, quantum communication. Madam has received many awards, namely Engineers Day Award by Institute of Engineers for outstanding contributions to engineering education on 15 September 2024, MTech Software Engineering second rank, VTU Belgavi on Feb 2000, Dr. Sri Sivaratri Rajendra Mahaswamiji Certificate of Merit for securing second rank in MTech Software Engineering JSS Mahavidyapita Mysore during 2002. Certificate of Appreciation for contributing to EMCC Academic Alliance Program Achievement Award, EMC Corporation 2010. Engineers Day Award, Lioness Club of Mysore 2012. Teachers Day Award, Mayuri, Lioness Club of Mysore South 2017. Best Paper Award title, A Reliable and Mobility Resilient Communication Protocol for Wireless Body Area Networks, AICT, sponsored National Conference on Research Trends in Computer Applications and Information Management, RTCAIM, during 2014. Best Paper Award title, Synchronous Optical Network to Deliver Quantum Information for Multiple Users, Quantum Communication Breaking Its Silence, Second International Conference on Data Engineering and Communication System during 2015. Best Paper Award title, Multicast QoS Routing by Using Network Processing Technique, IEEE International Conferences on Soft Computing and Network Security, SNS College of Technology, Coimbatore, in association with KYUNG POOK National University, South Korea, 2018. Elite Silver Medal for NPTEL Online Certification Course on Switching, Circuits and Logic Design, IIT Kharagpur, 2019. And certificate, the Bodhi Tree and Safe Tools for Effective Online Teaching, a hands-on workshop on 21st June 2020, Teaching Learning Center, IIT Mumbai, funded by the Pandit Madan Mohan Malviya National Mission on Teachers and Teaching, MHRD, Government of India, Certificate AICT Training and Learning Academy Online FDP on Computer Science and Biology during 2021. And Madam has published many journals, and Madam has also written many textbooks So there are around 40 to 50 textbooks are there, conference proceedings are there. She has published many journals and IEEE papers, study materials and textbooks, namely software engineering, computer organization, JavaScript, software engineering, advanced software engineering, namely, and many book chapters. And Madam has patent on scalable space structured ledger framework for industrial Internet of Things using blockchain. And resource person, she has been a resource person for several technical talks she was trainer, conference chair and sessions chair and reviewer for editor Springer lecture notes, AISS 2024, several reputed publications and academic collaborations. And she has visited Singapore, China, Australia, East Africa, IIT Kanpur, IISc, NITK, Anna University, JNTU, and many other places. And she has a Google Scholar ID and Scopus ID. And Madam is has having a wonderful profile. It's an honor to present your profile, Madam. Due to lack of time, I just read the shortened your profile and read. And if I done any mistake, apologies by my side. Thank you, Madam. It's really awesome to have you today.
Thank you. Thank you so much. Just a one line of introduction is sufficient that I am a teacher and I'm passionate to teach. That's it. I'm a passionate teacher. That's all my introduction. Whatever you said, nice of you. Thank you so much.
Thank you, ma'am. You can start the session.
Yeah. Okay. Good evening, one and all. I warmly welcome all the participants to the training, AICT Training and Learning ATL, sponsored 6 days online workshop on quantum computing, pioneering innovations in modern computer technology. I am thankful to UBDTT and UBDTT College, the authorities, for inviting me to this prestigious 6-day event, because it is a learning for me also. Preparing a talk is not that easy, as teachers, you know. So I put some efforts to bring in front many things, because my talk is an introduction. So I'm covering from day 1 to day n, complete concepts little bit, not completely, because all my colleagues will go in detail. So I'm going to give you an introductory overview of the whole topics in this case. So I hope you will really have fruitful session. So let me continue. In case you have any issue or any doubts, you can stop me at the end of the session. I'll be able to answer you. Shall I proceed now? It's visible?
Yes, ma'am.
Yes.
It's visible.
As introduced already, I'm called by name Vidyaraj. I'm at NIE since 1990, occupying various posts, and now I am heading the academic section as Dean Academic Affairs. And this is my 34th year of service at NIE. I'm very proud to say this. As a student of NIE, I'm continuing my work since 40 years at NIE. So my session today is on introduction to quantum computing. The very first question, like most of you are interested and you're today with us taking over for 6 days on this particular workshop, is because you know very well quantum computing is ruling us today, or it's going to rule us tomorrow also. Quantum computing is altogether a new way of computing. It could change the world and the way we think. It could transform medicine, break encryption, and revolutionize communication and artificial intelligence. Giant companies like IBM, Microsoft, Google, just to name a few of them here, are working towards building reliable quantum computers. Many countries around the globe have started investing billions of dollars for this emerging technology. India has also started setting up Quantum Research Center, as you are all aware of, and encouraging research funding under National Vision of Quantum Technology and Application Project. Scientists have promised that there will be revolutionized application for quantum technologies, just to name few of them, tracking the current bank security system and proposing a new ultra-secure form of cryptography, using quantum machine learning algorithms to enhance big data analysis, developing more secure blockchain technologies, simulating complicated chemical reactions to help in drug manufacturing, improving algorithms with application in supply chain management. See, the list of applications which will revolutionize our life further in future is endless. But with a few snapshot of this, I think it is time for all of us to make a shift from bits to qubits. I mean to say, from conventional classical systems to quantum and emerging technological systems. So let us start. To start with, I'm going to give you some few facts which will mesmerize you. Not only that, it will motivate you to take a step further in practicing this technology. So, what are these facts? Quantum computing is one among the world's top 10 emerging technology. I think all of you do Google. When you Google emerging technologies top 10, quantum computing is in that list. D-Wave, a company, was the world's first company to sell computers to exploit quantum effects in their operations to Google, NASA, and Los Alamos National Lab. Google, IBM, and Intel have all displayed quantum processors with around 50 qubits. Now it is more than 50 qubits, but this is the record that I'm going to give you. IBM Q from IBM is an industry-first initiative to build universal quantum computers for business, engineering, and science. D-Wave's latest quantum computer has 5,000 qubits that cost in millions of dollars. The first implemented quantum computing programming language is called as QCL. Government of India has complete focus on development of quantum labs. Now, what you're taking up a course is an MHRD and AICT initiative. So this is an MHRD and AICT are also initiating a lot of research funds, throwing funds to development of quantum centers. IIT, IISc, ISI, that is Indian Statistical Institute, BARC, IMI, Indian Mathematical Institution, and NITs. They're all encouraging interdisciplinary research. Just to give you a few IITs which are outperforming, IIT Roorkee, in association with Microsoft India, is offering quantum computing course for UG and PG programs. IIT Madras is giving you International Interdisciplinary Masters Program for I2MP in Quantum Science and Technologies. IIT Bombay offers a 2-year interdisciplinary dual degree course program in quantum science and technology. So these facts bring you in forefront and motivate you to the area of quantum computing and its applications. So this is a broad overview of my presentation. I'll be starting off with motivation, introduction, data representation, operations on data, problems on quantum computers, quantum algorithms, and finally conclude my talk. What motivates one to take up this field? I think you are all able to identify the leftmost diagram is nothing but Charles Babbage machine. We are aware that computer technology is making devices smaller and smaller. I request participants to please mute.
Dear participants, please kindly mute.
Yes. Computer technology is making devices smaller and smaller. The reason for this is we started off our systems, the technology from small scale integration. Today we are into very large scale integration. As you know, the technology has advanced. The devices are getting smaller and smaller. So how small is the question? The question right now is, the answer to that is, we have reached a point where classical physics is no longer a suitable model for the laws of physics. So we are at an atomic level trying to do something. The current drive towards increasing speed and miniaturization of computers leads the modern technology towards the subatomic domain called quantum computing. What is quantum computing? We can experience strange quantum behavior taking over from familiar classical notions. Now, in my next slide, I'll be differentiating classical notions against quantum notion. What is classical notion? The motion or dynamics of particles are described very accurately, and a given object is either a particle or a wave in classical notion. In quantum notion, the motion or dynamics of particles are described with probabilities. A wave is a particle and a particle is a wave, according to wave-particle duality principle. Feynman, the image is a scientist, Feynman, in 1982 proposed the idea of creating machines based on the laws of quantum mechanics instead of laws of classical physics. This gave way for evolution of quantum computers. Mathematically, if I have to define what is a quantum computer, quantum computers are machines that use the properties of quantum physics to store and perform calculations. Mathematically, a quantum computer is a probabilistic machine M given by M is equal to H, O, T, del, beta, where H is a state space of a quantum computer, O is a set of unitary transformations, T is a set of probabilistic measurement commands, del is an initialization operator, beta describes the final state. So what I am explaining is a theoretical model. It's a theoretical quantum computer. The next immediate topic that comes to our mind or a question is, what is quantum computation? The process of performing computations using the principles of quantum mechanics is known as quantum computation. In quantum computation, the fundamental unit of information is known as quantum bit, that is qubit. In classical machines, we use bit as a binary digit, which takes 0 or 1. In quantum systems, we use the word quantum bit, rather it is called as a qubit. Qubits leverage quantum mechanical properties to solve certain problems more efficiently than classical computers. So what we cannot do in classical systems are comfortably done in quantum system. That is the meaning of saying qubits leverages quantum mechanical properties to solve certain problems, not all problems, certain problems. In my slides to come, I'll be explaining what are the types of problems later. Certain problems more efficiently than classical computers. Unlike a classical bit, now I'm bringing you a difference between classical bit and a quantum bit through this slide. Unlike a classical bit, a qubit can be in a superposition state called as xi, a linear combination of states 0 and 1. So psi is represented as alpha of 0 plus beta of 1, where alpha and beta are probability amplitudes. 0 and 1 are computational basis states. Superposition is one of the fundamental principles of quantum mechanics that describe the ability of a quantum particle to be in combination of all possible states. It is because of this property we are able to achieve much more than what a classical system can do. So I'll be explaining this later. Next step. This is a diagrammatic view, the data representation of qubits. A physical implementation of a qubit could use two energy levels of an atom. One is ground state representing 0. The other one is an excited state representing 1. In the diagram, the leftmost diagram shows you that around the nucleus, you have an electron which is in a ground state. We call this as state 0. And when light pulse of frequency lambda is, the electron is exposed to light pulse of frequency lambda for time interval t, the electron moves from ground state to excited state, which is called as a state 1. In the next slide, I could tell you from state 0, we are moving into a superposition state. So instead of giving a light pulse of frequency lambda for a time interval t, We are now exposing the electron with a light pulse of frequency lambda for a half the time interval, that is T/2. When that is done, the position, that is, we are trying to enter into a state called superposition state. That is, the electron enters into a state, a combination state of what is called as a superposition, that is 0 plus 1. The ability for the particle, that is the electron, to be in the superposition is where we get the parallel nature of quantum computing. When we try to attempt to retrieve the values represented within superposition, that is, when an electron is in its superposition state, we try to retrieve the value or measure it, the superposition randomly collapses to represent just one of the original values. So this is a problem with the quantum systems. So what is the influence of superposition on its applications? As just now I told you, superposition allows quantum computers to perform computation on many possible states simultaneously. This parallelism provides a significant speed up for tasks such as optimization problems, where quantum algorithms exploit the superposition to search faster in an unsorted database. So when the database is sorted, we don't take that much time. When the database is unsorted, we require enormous time in classical system, which can be very comfortably done with a greater speed using quantum algorithms. Second example application is simulation. Simulating quantum systems in chemistry and material science is, because of superposition, we are able to simulate them very, very easily. So all the experiments I'll take you later also. This is an introduction slide. The next important concept I'm going to discuss is on relationship among data through entanglement. According to Einstein, it is nothing but a spooky action at a distance. So what is entanglement? Ability for pairs of particles to get linked and interact over any distance instantaneously. To become entangled, two particles are allowed to interact. First, we allow the particles to interact, then they are then made to separate. And the measurement of one particle is always correlated with the result of the measurement of the other particles. So this is called as entanglement, very important property or a phenomenon in quantum computing. Entanglement is used to set up a quantum communication channel used to realize quantum teleportation experimentally. What is the influence of entanglement on application? Entanglement is a basis of many quantum computing applications, such as, I'm just taking sample examples, but there are plenty of applications are there. One is quantum cryptography. In protocols like quantum key distribution, called as QKD, entanglement ensures secure communication by detecting eavesdropping. Quantum teleportation. It enables the transfer of quantum state over long distances, forming the basis for quantum internet. In the next slide, I'll be discussing about quantum teleportation also. The third application of entanglement is error correction. Quantum error correction relies on entanglement to detect and fix errors without destroying the quantum information. It's very important. Without destroying the quantum information, can we fix error? Can we find out errors? That is what the entanglement helps us. Parallel computation. Entangled qubits. Once the qubits get entangled, they allow simultaneous processing of correlated data, making Shor's algorithm more efficient for factoring large numbers. I just used the word quantum teleportation in the previous slide. What exactly it is? It is a very important concept in quantum mechanics, which provides a mechanism of moving a qubit from one location to another location without having to physically transport it. Is it not a phenomenon? Without transporting the qubit, still we are able to utilize the benefit of it, because it uses quantum entanglement between sending and receiving location. In 2019, Japanese researchers carried out quantum teleportation within a diamond. So using the diamond as the atoms or the molecules of it, they were able to carry out teleportation and study the experiment. What is the influence of teleportation on applications of this? Quantum teleportation is a foundational technology for applications such as quantum communication. We can build a quantum internet with this, where quantum states are transmitted over long distances without direct transfer of particles. Quantum key distribution, QKD, the quantum teleportation enhances secure communication by allowing encryption keys to be distributed securely without the risk of interception. Again, I'm just telling you more information or more technicalities will be discussed by my colleagues, other resource persons in the days to come on QKD, quantum communication, all these things in detail. Distributed quantum computing. This allows quantum processors at different locations to share information, quantum information, enabling collaborative computation across a quantum network. Error-free state transfer. Since teleportation doesn't involve physically moving the particles, it avoids noise and decoherence over long distances. So noise can be minimized. The next important concept is quantum interference, a phenomenon in quantum mechanics that arises from the wave-like nature of quantum particles such as electrons or photons. When a particle is in a superposition of multiple states, these states can interfere with each other, leading to constructive or destructive interference. Constructive interference amplifies the probability of certain outcomes, while destructive interference cancels out others. So interference is a very important phenomenon which makes our multiple state work better with minimum interference. What is the influence of this on application? Interference is important for quantum algorithms to coverage on the correct solution. One example algorithm is Grover's algorithm. This uses interference to amplify the probability of correct search result while cancelling out the wrong solution. This provides a quadratic speedup for search problems. Error migration. By carefully handling interference, errors caused by noise in quantum circuits can be reduced or cancelled out using this technique. Optimization problems. Many quantum optimization algorithms rely on interference to highlight optimal solution while suppressing suboptimal ones. That means the most important optimal solutions are given importance, not the suboptimal ones, using the technique of interference. So next, I'm going to go further and talk about one scientist, that is theoretical physicist David Dutch. So he is very important because he is called as the father of quantum computing. He is from Oxford University, a theoretical physicist being called as the father of quantum computing because of his enormous contribution to the field. In 1985, he developed the quantum Turing machine, showing that quantum circuits are universal. In order to claim quantum systems are universal, we need to look at the gates. So how do we operate on data? Using quantum gates. What is a quantum gate? A quantum gate is a device which performs a fixed unitary operation on selected qubits in a fixed period of time. Based on the number of quantum bits or qubits used for operation, we can classify quantum gates under two headings: single qubit gates and multiple qubit gates. Single qubit gates, they operate using single qubits. Some examples of single qubit gates are NOT gate, the Hadamard gate, Pauli gate, phase gate, and pi/8 gate. Just for sample sake, I am going to take one or two sample gates and explain its operation. The details are again available in the next sessions to come on the logic gates. The NOT gate. The quantum NOT gate is also called as an X gate or a poly X gate. It performs bit flip operation. That means if you give an input 0, computational basis state 0, it flips to 1. If you give 1, it goes to 0. So matrix representation of that is X, is a 2 cross 2 matrix as indicated. When this gate is applied to a quantum state psi, alpha of 0 plus beta of 1, it transforms the state psi to alpha of 1 plus beta of 0. That means it is flipping. It is performing a bit flip operation, and it is the circuit of that is represented as shown in the diagram. The next one is a Z gate, also called as a Pauli Z gate. This gate leaves 0 unchanged and flips the sign 1 to -1. So you can see in the diagram, alpha of 0 plus beta of 1 gives an output of alpha of 0 to beta of minus beta of 1. When this gate is applied to a qubit in a state psi, alpha of 0 to plus beta of 1, it transforms the state as Z. That is, the Z gate transform is equal to alpha of 0 minus beta of 1. So this gate is, where do you use this gate? This gate is used for what, to correct the unitary error in the circuits, and also for superdense coding. The technique called superdense coding, to encode 2 classical bits into 1 qubit, we use superdense coding, for which Z gate is used. The next gate is a Hadamard gate. This gate is also known as square root of NOT gate. And this matrix is represented as H is equal to 1 by root 2 of the given 2 cross 2 matrix. And the circuit, you can see alpha of 0 plus beta of 1 for putting on to Hadamard gate gives you alpha of 0 plus 1 by root 2 plus beta of 0 minus 1 by root 2. That means to say that it turns 0 into 0 plus 1 by root 2, 1 into 0 minus 1 by root 2. This gate is used for quantum error correction, also to perform basis transformation, and this is responsible for creating superposition. Next, we move on to multiple qubit gates. 2 or 3 qubit quantum gates are multiple qubit gates. Examples, two examples I'm giving here. For a 2 qubit gate, the example is a C0 gate. 3 qubit gate is a Toffoli gate or CC0 gate. The C0 gate is nothing but controlled NOT gate. It is also called as a XOR or a measurement gate. In this case, this is a 2 qubit gate because we have 2 input qubits. One is called as a control bit, the other one is called a target bit. A, in the circuit, A, the connection to A is called as a control bit, B becomes a target bit. How does this gate act? The action of the gate, it goes like this. If the control bit is set to 0, then the target bit remains the same. Look at the first topmost 2 qubit state, 0, 0. It remains as 0, 0 in the output. If it is 0, 1, in that case, because the control bit is 0, the target bit is also 1. If the control bit is a 1, the target bit gets flipped. That means for 1, 0, the output is 1, 1. If the input is 1, 1, the output is 1, 0 because the second bit, target bit, is flipped. So this is a C0, a very important gate meant for measurements. Next is called CC0, that is controlled NOT gate or Toffoli gate. It's also called Toffoli gate. It's a 3 qubit gate with 2 control bits that are unaffected by the action of Toffoli gate. The third bit is a target bit that is flipped only when the first 2 bits are 1, 1. So this is a Toffoli gate. You can see here. This gate can be used to simulate NAND gate operations. We have A, B control, the C becomes the target. So this is a quantum circuit. Collection of quantum gates interconnected by quantum wires is called as a quantum circuit. I think you can make out we have one H gate, that is Hadamard gate, and two C gates in this case. So they are all connected by wires. They are all initialized to 0 state 0, 0, 0. An important qubit state defined as a maximally entangled quantum state of 2 qubits is called as a Bell state. Here and there you will be listening to this state. It's a very important state as far as the state of the qubit is concerned. It is a key ingredient in quantum teleportation, which is represented as 0, 0 plus 1, 1 by root 2. I'm not going to the details of this, just you have to know what is a Bell state. So this is a circuit diagram of Bell state with a truth table given like this. And the interpretation is 0, 0. When I'm giving the input as 0, 0, what happens and finally what is the output? We are going to get as 0, 0 plus 1, 0 by root 2 transformed into 0, 0 plus 1, 1 by root 2, which is nothing but Bell state 0, 0. So coming to the first part of it, I'm going to now distinguish between whatever you listen to me now. Let me summarize the difference between classical bits and quantum bits. Classical bits can exist in 0 or 1 state that you are aware of. Quantum bits can exist in state 0 or 1 or in superposition of 0 and 1. Classical bits, n bits represent one of the 2 power n combination, where n qubits represent all of the 2 power n combinations simultaneously. Classical bits can be measured completely, whereas quantum bits can be measured partially. Classical bits are not changed by measurement, whereas quantum bits are changed by measurement because they collapse. Between the classical logic gates and quantum logic gates, classical logic gates are irreversible, that you are familiar. Quantum logic gates are reversible because of unitary constraint imposed on them. Only single bit gate, classical gate, is a NOT gate, but here we have many gates like X gate, Z gate, H gate, etc. The difference between classical circuits and quantum circuit is that classical circuits are cyclic, that is, they have loops or feedbacks, whereas quantum circuits are acyclic, no loops are allowed. When you come to operations of fan in and fan out, classical circuits they allow fan in, fan out, whereas quantum circuits, there is no fan in, fan out operations allowed. So now I'm going to the next topic, that is the power of quantum computers. What makes you to think about quantum computer? What advantages do they bring to our applications? I'm comparing this with our traditional computers and making the statement. Ability to access and manipulate arbitrary superposition of states, a feature known as quantum parallelism, is what makes quantum computers very powerful, because quantum gates can perform many logic operations in parallel. The second power is the ability to solve problems with varied computational complexities. That means problems which can be solved using resources which are bounded by a polynomial in n, problems which require resources that grow faster than any polynomial n, which are called as hard problems. The hard problems, or NP hard problems, become the key candidate for quantum computers. So ability to solve these type of problem is that makes quantum computers more powerful. The next power is with respect to large memory space. It is possible for us to enhance the memory space, what we call the Hilbert space here. The state space H of a quantum computer is composed of n identical subsystems given by H is equal to s to the power of s raised to n, wherein we are using a tensor operator in this case, s tensor, s tensor, s. That is, look at the example, the computational basis 0 tensored with 1 gives us a dimension, a larger memory to occupy 2 qubits 0, 1. A 0, 0 tensored with 1, 1 gives us 0, 0, 1, 1. So this is how we can say that the Hilbert space is what makes us give a large memory space the power of quantum computers. Coming to the limitation of quantum computers, the first limitation I already explained is quantum measurement. Quantum theory works on the hypothesis that observable quantities vary distinctly in quanta. When an observation or measurement is made, the system collapses into one of its possible computational basis state, losing the state of superposition. This I have already explained through a diagram. When we try to measure a particle when it is in the superposition, the measurement makes the system collapse to any one of the computational basis state, either 0 or 1, thereby losing all our measurement. The next limitation is decoherence. This is the interaction of a qubit that has with its environment causes disturbance, and because of that, it collapses superposition. The environmental disturbance can make the superposition collapse, leading to decoherence. Now coming to what are the candidates or the problems that we can solve on quantum computers. I just made a mention, computationally intense problems are the candidates because they require exorbitant resources, both time and memory, for their solution, which are impossible on a classical computers. So such problems, some examples I've taken here, I'm just listing them: order finding, factoring, discrete logarithms, searching of unsorted database, graph connectivity problems, perfect matching of graphs, K-Clinks problems, lattice problems, graph isomorphism problem, group problems, some of them, etc., etc. So these are the problems on quantum computers which require attention of quantum algorithms, because these problems are hard problems and require exorbitant resources for their solution, which are impossible on classical computers. In the next slide, we will see a sketch, a figure that states the knowledge about quantum algorithms, which we can broadly classify them under two headings as quantum Fourier transform algorithms and quantum search algorithms. So this is a sketch taken from a well-known textbook by Neil and Chang book. I've adopted the same diagram. Quantum algorithms with notable application. To the left of the diagram is a Grover's fast quantum algorithm with applications for statistics, mean, median, and minimum. It can speed up some NP problems and search for crypto keys. And the fourth application where we can apply fast quantum algorithm Grover's is quantum counting. The Peter-Shor's quantum Fourier transform algorithms can be applied to quantum counting, discrete logarithm, order finding, hidden subgroup problem, what is called as HSG, and also discrete logarithm and order finding together find their application for factoring. To break RSA algorithm, break crypto system like RSA, we have to use discrete logarithm, factoring, and order finding algorithms. This is just a snapshot of the algorithms with notable application. We'll just take one by one little bit. This is an image of Peter Shor, a very well-known scientist, quantum scientist. In 1994, Peter Shor discovered an efficient algorithm for factoring large numbers. The algorithm, again, you have a session on Shor's algorithm and Grover's algorithm. I will not go into the details of that. Just I will tell you two steps, important steps here. The first step is converting the factoring problem into problem of finding the period of a function, and this, it is implemented classically. It may be implemented classically. The second step is finding the period using quantum Fourier transform, and this step is responsible for quantum speedup. So step number one is implemented classically. Step number two using quantum algorithm. This is the second step which brings you quadratic speed for the algorithm. So this is a performance comparison of Shor's algorithm with other factorization algorithm. We have taken some known algorithms like quadratic sieve, generalized number field sieve, and special number field sieve, meant to factor the numbers, that is number of digits. Just to give you an analogy, for a 300-digit number, public key size being 300, number of bits approximating to 1024, the timeline for generalized number field sieve is yet to crack, that is efforts required, that is MIPS per year, is 10 raised to 11. For special number field sieve, that algorithm for same 300 digit 124 number of bits approximately, the efforts required is 10 power 7 years, MIPS per years. 300 public key size 300, number of bits 1024, less than 1 second it has taken by the Shor's quantum factorization algorithm, and it was proved in the year 1994. So this is because of Shor's quantum factorization algorithm, there is a probable threat for most of our public key systems, including RSA. This is again other view of it. The performance of factoring a 300-digit number on classical computer and a quantum computer, the best classical algorithm takes 10 power 24 steps as operations and 10 power 10 steps using Shor's quantum algorithm. The speed is 150,000 years for best known algorithm classically, and less than 1 second using Shor's quantum algorithm. The next important algorithm is by Low Grover. In 1996, he created a fast quantum algorithm for searching the unstructured database. To search n items, classically it takes O of n. That is, I'm talking about the time complexity in this case, and quantum takes O of square root of n times. So this is shown indicated using the results. Just to give you one small example, for the size of crypto key to be searched in bits, I'm talking in bits, 10 bits requires number of possible keys generated, that is n is 2 power 10, 1024. The search of keys, the crypto keys using classical search is O of n, 1024. The speed of searching the crypto key using quantum search is O of root n, which is nothing but 32. So enormous, tremendous amount of speed we can get into while we are going for unsorted searching of database. So now the next important question that comes to our mind is, why are factoring and searching unstructured database problems important? As I already told you, they are hard problems and require exorbitant resources for the solutions which are otherwise impossible on a classical computer. This statement gives us an idea that quantum computers may be inherently more powerful than classical computers. So I've just listed some of the key candidates for fast quantum algorithms with field and study of application. Suppose we take the field of study as cryptography. The candidate for fast quantum algorithm is order finding problem. What's the application? Breaking RSA crypto system. Suppose you take the field of study as cryptography, again factoring problem, it can break RSA crypto systems. Cryptography discrete logarithm problem, it can break Elgamal crypto system. So like that, I have listed cryptographic applications and graph theory. If you take the Hamiltonian cycle problem connected to graph theory, it can speed up algorithms for some problems in NP. And also, if you have graph theory, very important application, candidate would be graph isomorphism, which is meant for designing of our networks. So cryptography or graph theory, quantum computing can estimate number of solutions quickly, checking for existence of non-existence of solutions. So this is just a snapshot of some of the key candidates for FQO. People who are researchers can look into the table and you can take a problem statement on any of the candidates for FQ and develop an application on it. Now, what are the prospects of quantum computing? The prospect is that we are at a position to say we have a threat to network security and e-commerce application, because we just saw it is possible to break RSA algorithm in seconds. We also have threat to our digital signature. All our Aadhaar cards and other digital signature are at a stake because we are bound. We are already trying to break Elgamal crypto systems with our quantum systems. An attempt to solve an NPC on classical system. That's a prospect. Introspection, we are able to introspect on what kind of problem can a QC solve in future. That is also known to us. Now coming to the next section, physical systems for implementing QC. Again, you have a separate session on the physical system. What is a snapshot, whatever I am giving you. Superconducting qubits. The circuits created using superconducting materials that can exhibit quantum mechanical properties for applications in quantum chemistry, optimization, cryptography, and artificial intelligence. So circuit created using superconducting material. What are superconducting material? Examples of them are like niobium and tantalum. These are the superconducting materials which can exhibit quantum mechanical properties and they can be used. And when we say superconducting, they are going at minus degree Celsius or Fahrenheit. That's the degree at temperature through which we can perform operations. Trapped ions. Individual ions, which are charged atoms, are confined and manipulated using electromagnetic fields for applications requiring high accuracy and precision for quantum metrology and error correction. Photonics. Photonics-based quantum systems use properties of photons to encode, transmit, process quantum information, are well suited for communication, networking, and computational tasks. Topological qubits. The word topology is connected to mathematical area I'm talking here. The use of principles of topology to create stable, error-resistant qubits to achieve fault-tolerant quantum computation with fewer resources for error correction. So I have discussed 4 important physical implementation of QC. Next, in order to build a physical system, what are the challenges? The first challenge is noise and decoherence. Decoherence I've already explained. Qubits are extremely sensitive to their environment, which can introduce errors. Scalability. Building a large, reliable quantum computers with many qubits is technically challenging even today, even for the day. Error correction. Quantum error correction is more complex than in classical system due to the very nature of quantum states. The next is experimental realization. Where are we in experimental realization? The demonstration of the world's first 2-qubit quantum computer in 1998 happened at University of California, Berkeley. Demonstration of Grover's database search algorithm happened in 1999 with 3-qubit quantum computer. Demonstration of order finding algorithm in 2000 with a 5-qubit quantum computer. Demonstration of Shor's quantum factorization algorithm happened in 2001 with a 7-qubit quantum computer. Google announces the creation of a 72-qubit quantum chip called Bristlecon in the year 2018. IBM unveils its first commercial quantum computer, the IBM Q System 1, in 2019 and in 2020, respectively. 65-bit qubit QC is also announced or unveiled. So what's next with all these experiments that have been carried out over years? The next is commercial quantum computer. Is it a dream or a nightmare? While the potential for quantum computing is huge and recent progress is encouraging, some commercial quantum computers are available are in available form with companies like IBM, Microsoft, Rigetti Computing, D-Wave, and Google. While NMR-based systems, that is NMR stands for nuclear magnetic resonance systems, they are still laboratory experiments earlier are now commercially available as 2-qubit desktop quantum computers called as SpinQ Gemini. IBM made its aspiration more concrete by publicly announcing a roadmap for development of its quantum computers. So if you go to IBM quantum computing, that is, you just type IBM quantum computing, you get a roadmap. They have put a beautiful roadmap for the years to come, which talks about the development roadmap, also the research roadmap. Please have a check on that. IBM Quantum Heron the company's most performant quantum processor to date and available in IBM's global quantum data centers, can now leverage Qiskit to accurately run certain classes of quantum circuits with up to 5002 qubit quantum operation. So this is the latest development by IBM. The next topic is quantum simulators. What are quantum simulators? The tools to develop and test quantum algorithms to simulate physical models for the hardware implementation of a quantum processor. We have a separate, I heard that we have a separate session on quantum software and simulators. Our resource person will take you through that in detail. This is just a snapshot. Only 3 examples I am citing here, which are nothing but Qiskit from IBM. It is an open source quantum computing framework by IBM for simulating quantum circuits, quantum chemistry, and material science problem. We can carry out chemistry and material science problem using Qiskit. CirQ is from Google. It is a Python framework for designing, simulating, and running quantum circuits. This is useful for quantum simulation tasks like quantum dynamics and many-body physics. Next is SimulaQuron, a distributed quantum network simulator for simulating quantum communication protocols and networks. So in all, quantum simulators are very, very handy tools that are developed. Many companies have come out with developing the simulators, and we can test the algorithms. You can get to know the feel of a quantum computer by doing it. So, but the only thing is the limitation is on the quantum hardware. Immediate question that comes to our mind is it possible to simulate a quantum computer on a classical system? If I ask you a question, you have to think and answer. That's why I put a question mark, but the answer is ready there. Yes, it is possible to simulate a quantum computer on a classical system. Why is it possible? Because the existence of reversible Toffoli gate. Because of the Toffoli gate, I told you quantum circuits are reversible. Because of that, it is possible to simulate a quantum computer on a classical system. But, however, efficient implementation is not possible. This is due to the stochastic nature of quantum measurements. The immediate question after this is it possible to efficiently simulate a classical computer on a quantum system? The answer is obviously yes. It is possible to efficiently simulate a classical computer on a quantum system. I have not much to say, but some pictures here. A dream come true. IBM's test tube quantum computer, Dr. Isaac Chang, a leading quantum scientist. He's one of the authors of the very well-known book on quantum computations. The very first book introduced with a lot of research material in that is by one of the authors, Dr. Isaac Chang. He is holding a vial, one of the powerful quantum computers, a solution containing a billion molecules that act together to calculate exponentially faster than conventional computers. This is an image of IBM's 7-qubit quantum computer loading Shor's algorithm for demo purpose. Here, Isaac Chang is using Shor's algorithm. It was possible for a quantum computer with 7 qubits to factorize numbers 15. They were able to factorize number 15 into 3 and 5 factors. This is the action of Shor's algorithm. IBM 7-qubit molecule, the world's most advanced quantum algorithm. The researchers at IBM use this computer to conduct the first demonstration of Shor's quantum factoring algorithm for factorizing number 15. So this gives us an idea we are towards quantum simulation. I have come to a conclusion. I think, well, I'm closing little early. Is it okay, madam? Because I can take some questions after this.
Yes, ma'am. You
Okay.
you take some questions and we'll have a feedback.
No,
and then we'll close.
I've got few more slides, not exactly the conclusion. I have few more slides here.
Okay.
Conclusion is, with a start to explore some of the wonderful contributions of quantum Fourier transforms and Shor's and Grover's algorithm in particular, the future is turning quantum computation into engineering reality. So when I say towards reality, we have to have a scope for further work. What is that scope? To develop efficient quantum, see, we have quantum algorithm, we can write quantum algorithm, but how efficient are they is what it matters. To develop efficient quantum algorithms for problems that apparently do not have efficient solution in classical computing and do not appear to be NP complete either. So such problems become the key candidates for our scope of future work. What are these problems? Lattice problem and code problems. Problems in lattices have application to cryptography and coding. Such problems include approximating the shortest vector in a lattice. Next is graph isomorphism. Given two graphs describing a relational structure, are they equivalent up to relabeling? So it's a big problem. This problem has drawn attention as a most natural, likely to have an efficient quantum algorithm. The next problem is group problems. Graph isomorphism is an example of a more general hidden subgroup problem called as HSG problems. To these and related group problems, do we have good quantum solutions? Is a scope for further work. Simulating physics. How efficiently can quantum algorithm simulate quantum and classical physical systems? So there is a scope for you to work on this. The next important part where a scope exists is, can we look at an alternate tool to QFT for better efficiency? QFT stands for quantum Fourier transforms. Can we have a better tool alternate to QFT so that we can achieve better efficiency? So these are some of the emerging areas where the scope of whatever I spoke about can exist and continue to be worked on. One is encryption technology. The other one is communication technology. Next is molecular simulations. Then DNA computing, computer graphics, traffic optimization, weather forecasting, climate change, and many more. So what is encryption technology here? How can I use quantum systems or quantum technology for encryption as a basic encryption methodology? Encryption technology uses quantum mechanics to secure data and making it harder to break than our conventional or traditional systems. So if we can make our systems more secure using the encryption standards, or I can make encryption technology is one of the emerging technology in near generations. The second one, as I told you, is communication technology. This technology uses quantum mechanics to transmit and process information. More specifically, I can talk about photons in this case. So photons become very handy, transmit qubits on the communication channels. But today, channels are also not safe. So we have to look at noises. Noises are prone in channels, communication channels. So we are trying to experiment, we are trying to do a lot of research to make our quantum communication channels noiseless. So you have scope for doing research in this area also. The next is molecular simulations. We are trying to simulate molecules and materials at an atomic level. So this particular simulation task is very, very beneficial in the areas of the pharmaceutical industries. Drug discovery is happening. A lot of drugs are being discovered at the atomic level. We have to perform a study. And not only that, we can study electron to electron interactions using this simulation. Just to give you an idea, a simulation run on a classical system with our existing hardware may take a week or 15 days to get a result. Suppose I'm trying to discover a molecule, I'm trying to interact with a molecule. Rather, if you put the same simulation on a quantum system, it can produce you result well within minutes. So this is what is molecular simulation with a lot of applications. The next is DNA computing. As you know, DNA computing is not exactly a direct application of quantum computing. It is also one of the forefronts. We have what are called as beyond silicon computing. Many techniques of beyond silicon computing compared to our conventional system. This quantum and DNA are having a lot of potential. Even DNA computing is meant to create a lot of results in connected to genome sequencing. Also, we can say genome analysis. So you know that DNA has a lot of material, so which takes the encoding of DNA is very, very difficult, and to decode also it is very tough, but people are doing it. So genomic sequencing, genome analysis can be very comfortably done because it involves a lot of data. Quantum computing is a perfect choice for that. The next is computer graphics. I mean, graphics means lot of images, lot of data collections, and you have to link one object to other, where animation do play a lot of role. So quantum computing has a lot of help in that. And traffic optimization. Calculation of fastest route, optimizing the multi-bit variables is possible using this. When traffic optimization becomes a solution, I think we can do wonders in our traffic engineering. Weather forecasting and climate change is the last emerging technology area I'm going to talk about. As you know, weather forecasting is a real-time application, wherein we collect lot of data from sensors, real-time data, taking the data, storing the data, and analyzing the data. As the word forecast mean in this case, heavy data requires to be analyzed, and it also requires some amount of sorting of the unstructured database. Not only that, we will be getting an unanticipated or anticipated events have to be done. Anticipation of the events accurately is very important. In that case, the key candidate would be a quantum algorithm here. And when you come to climate change, we need to reduce carbon footprint. So quantum computing or quantum technologies are towards development of what you can say energy, batteries and other energy generating systems are being focused on. A lot of research is happening in that direction, where we are trying to create new energy production technologies, and also we are trying to conserve energy by way of quantum systems. So these are some of the emerging areas, and many more are there. That's why I put the dots there. So some of the emerging areas where lot of innovations are happening, lot of research is happening. So some of the major quantum research centers in and around the globe I have just listed for you to know. IBM Corporation USA, Max Planck Institute Germany, MIT USA, University of Waterloo Canada. See, when I started my research way back in 2003, University of Waterloo was the only university where a lot of research material were available for me, and many researchers were there from Waterloo. Even today it is number one, I can say. Then Masaryk University, Z, that is I'm talking about, Czechoslovakia Republic, that is one. University of Bristol, UK, Imperial College London, Osaka University Japan, Intel Corporation USA, and Google, of course, and NVIDIA. You can even add the list NVIDIA in this case. And of course, when you come to our own institutes, higher learning institution, ISC, when I was a student, I have visited a couple of times to theoretical physics department, and also to the physics department, where they were trying to develop 2-bit systems, that is not gate and AND gate. I do remember still going and having a talk with them, scientific talk. IIT Madras, IIT Delhi, IIT name any IIT today, it has all the quantum research. IIT Kanpur, Raman Research Institution Bangalore, the Institute of Mathematical Sciences Chennai, Indian Statistical Institute Kolkata, and today most of our NITs are also having lot of research happening in quantum. And why not? Even our VTU, proud VTU, is conducting a lot of research, is having a lot of research initiatives in quantum systems. So these are some of the references and acknowledgements from the books and materials that I have taken. And one prominent website is qubit.org, and other links I have referred to, and journal. And as I told you, the IBM's announcement of Feynman website, Peter Shor's algorithm, Bennett algorithm, many journals I have referred to. I have listed few of them. So according to me, this is not the end, but the beginning of whole new era of computing. So according to me, I think I just happen to say thank you for all of you for listening to my scientific talk. Maybe if I've made any mistakes during my talk, please pardon me. I'll be very happy to listen to you, any feedback or any questions. So I've just, I think I'm little early. I closed little early, about 20 minutes early.
It's okay, ma'am.
Anything that you would like to like me to repeat, I'll be happy to do that again, in case any participant would like to see any slide again.
Firstly, Kanya ma'am.
Participants, any questions?
Namaste, Vidyaraj madam.
Namaste, sir.
Namaste. I'm very happy to know that you have introduced the quantum computer into our audience. My question is, can you think all our present classical computers are replaced by quantum computer?
I mean, a day will come, sir, or any replacement. As of now, it is not possible. See, what we can think is, we call that as a hybrid mode, hybrid machines. For our classical system, because speed of our classical system is a limitation. We don't have that process right now. It's like a day was there when we never thought of a pen drive. So a coprocessor or all that we didn't think. So just like that, on our classical system, we already have some chips available with us. Putting that chip as an extended processor, it is possible to simulate a system, quantum system, but as of today, replacement is really tough. So that's the reason our experiments or all our laboratories are focusing on hybrid machines. But in years to come, definitely will be replacing. I'm talking about another 10 or 15 years from now, 2040, that it is possible. We will be very happy to say our systems will be quantum systems. See, when I did my research, 2003, again, I'm coming because I'm probably one of the oldest person here. In VTU, I'm talking, not in other IITs. In VTU, I think I and my one more professor, late H.D. Panindra, we were the only two to conduct theoretical research on quantum system. In my thesis, I clearly mentioned, saying that with all the materials that we had, we referred to, I and my guide were able to predict that in 2025, the quantum will boom in academics. I think we are close to that. So it is possible to get it in near future, sir. As of now, it is only possible to have a chip, a small chip, which can speed up certain process only. I think I have answered your question.
Yes, madam, you
Sir,
answered it.
So in 2008 only, Japan came up with a quantum chip. Okay, that could be put in a classical system, but the speed of our classical processor was a hindrance to that. Not much I could gain as a speed, but definitely it was possible to adopt as a co-processor.
Thank you, madam.
Thank you,
I
sir.
think as you wish, all the speed of the machines will go to a greater extent. Nobody has imagined. All our NP hard problem will be get solved, if I am
Yes.
correct.
Yes.
Thank you, madam. Thank you very much.
Thank you.
Ma'am, one of the participant has posted the question in chat.
Yes.
In healthcare application, can you let me what major thing we need to do?
Yes. In healthcare application, if you take, one is you can think, see, when we try to, one is acquiring data. We have a lot of data in our healthcare applications. That is, if you take a scan, if you take a medical record, I'm talking about the storage, a part of it. If you take a scan and store it, data is enormous. So how to protect the data? That is one thing. Number two, if you want to transmit the data from healthcare data, which is secured, you need to develop lot of secured algorithms. Encryption plays a very important role, quantum encryption. So we know that our algorithms, like Peter showed, can break the most important cryptographic algorithm within seconds. So how securely you can transmit data is a challenge that is ahead of us. So in healthcare, what is important is protecting our healthcare data and transmitting it over communication channels, because noise should also not get added to our data when we transmit. See, the data that any image, I'm talking about, let us say, scan report sent from this place to another place. So that confidentiality and the data should not be corrupted. So uncorrupted data in real-time application should reach the destination correctly in time without any false play. So encryption plays a very important component, and because of the threat of quantum system, we should come up with a very, very good and an efficient quantum algorithm so that break is not possible. As of now, I could only sense these two applications.
Thank you, ma'am.
Okay, ma'am.
Nayana, madam.
I think just to be, I don't know, just what is coming to my mind, I can tell you. In the days to come, in the years to come, not days, the years to come, or maybe next generation to come, we may have a quantum computer, as because it is at atomic level, there may be no scans, no scan, medical, I'm talking about the healthcare system, no scans, no injection. Just now they are passing what you call that, I forgot, the heart, to have a block. If they have a block, they pass the needle and try to check. Okay, the scanning technique is there. Just like that, we, instead of making all the process like that, looking at a block, laparoscopic method or any method like that, a small vial of atom, a liquid is given, so you can drink or inject a particular atom to a specific location. The system will regenerate and create a computing device for you. You yourself become a quantum computer. That is my vision. It is not real. It is, what you can say is like a a movie or animated concept I am giving you. Just taking a vial, getting injected to a part of a brain or a heart or something like that, the system will just regenerate. It will start making work the way as a computer or a bits, the qubits. They can interact, they can communicate. You can put a sensor, quantum sensors, you can go ahead. And it's not real, but virtually I am visualizing at right at this moment. It is possible in generations to come, all our systems are replaced by liquids or atoms. How correct I don't know. Please excuse me, this is what I am visualizing right now.
Okay.
Next
Naina,
question is we can connect a Raspberry Pi to unmute ಮಾಡಿ ಮೇಡಮ್ ಅವರೇ ಕೇಳಲಿ ಕ್ವಶನ್.
ಅದೇ ಅವ್ರು ಕೇಳಿ, please unmute yourself and you can ask the question. Naina and Manjunath sir.
Yes, please.
Madam, good evening.
Good evening, sir.
Madam, I have one question. Especially in modern era, whenever new technology comes, and it is usually breaking the traditional encryption method. What is the security measures it is having? Because every new technology is having some security measures. How a quantum computing is having that much security so that the third party cannot hack it?
Sir, that is where we are working on different layers of security, sir, through algorithms. So one is the hardware part, the other one is the software part. Okay, so as of now we don't have much experimentation done. Experiments are still in process because we have many algorithms like BB8 and all that algorithms are there, sir, which actually protect us. But protection and security are two different things. Lot of research is happening in that area, wherein we are developing efficient algorithms for protecting our systems. That is, encryption systems are in place. But as of now, experimentation is still going on, sir. We cannot rightly say this is the solution. Lot of research is happening. And like I can say, even in communication systems, for nearly 15 meters, the communication can just happen after 15 meters, it is weak. That is, we need to repeat it, we need to amplify it and send. By that time, when the signal becomes weak, somebody can get into the system. So experimentation is on, demonstrations are yet to come. But other side of it, software developers are developing their cryptographic algorithm, trying to make them more secure.
Thank you, ma'am.
Thank you.
Naina ma'am, do you want to ask any question?
No, ma'am.
Okay, one more question, madam. Can we connect Raspberry Pi to quantum computing?
Madam, Raspberry Pi, if it is working on a classical system, there is some problem. You can only connect through simulators. You can run simulators and do it. There is nothing like a quantum system here. Your classical systems will have simulators. You can simulate it, but again you require an interface for that to match the speed. So you have to develop an algorithm which can connect that to this.
Madam, next question. Quantum simulator CIRQ, how to use it? Circuit.
I don't know, madam. I have not used it because I have used other simulators, not that, just have listed. I think we have a resource person, that's what he told me. He's going to deep on simulators. Probably you can post this question there.
Okay, ma'am.
I'm sorry, because I have not used it.
It's
I
okay,
cannot
ma'am.
explain on that. I have not used it.
Okay, one more question is drug discovery, how it will be helpful? This concept, how we can use for drug discovery and all.
See, I told, again, I'm not a very expert as a chemist to talk on that, but still I'll try to attempt. See, madam, we had COVID vaccines and other things developed, as we all know. We have undergone all that situation. Had the discover, that is, trial and errors have to happen, and simulation is one thing that takes weeks and months to get a proper result, and to rerun it again and again takes more time. So getting that is, see, what I can right now tell you is drug discovery time taken to simulate and get the result will be faster in a quantum system. Same thing if you experiment using a classical system and simulate, it will take months and years. So you can get the result faster. That will help us to know our drugs faster, because it's a molecular interaction what we are talking here. See, all this, the results are, see, speed up is the only thing we can expect from a quantum system, nothing more than that. Speed. If you want anything faster, we have to go for quadratic speed, means we have to go for one type of algorithm. If you have to go for I forgot. Yeah, basically drug discovery is the only thing possible because of the speed of the system.
Ma'am, what are the major contribution the quantum computer has contributed towards the artificial intelligence, ma'am, advancement of artificial intelligence right now?
Madam, I'm not able to talk on the AI field right now, because machine learning, quantum machine learning, the machine learning algorithms have been developed.
Okay.
And we are able to use that for healthcare also, for defense purpose also.
Okay.
Okay, not directly AI I can talk about. Machine learning algorithms through quantum. We have quantum machine learning algorithms in place.
Okay.
Lot of research is happening in that direction for the problems which require enormous resources. For that, quantum becomes a candidate. Otherwise, no. If I'm able to solve within the given resource,
Okay.
quantum is not required. You can do it classically.
Classical.
Yeah. If you have enormous, see, you want to break something within a second, which is not possible, only then you bring in quantum system there. Every time quantum, using a quantum system for which is not required takes you money.
Okay.
So that is where a proper decision has to be made. Speed is required, apply quantum algorithm. Speed not required, go for a classical algorithm. So via media is our hybrid algorithms.
Okay.
Only speed up, you use quantum systems.
Some,
Is it in
Madam,
the
if
times
you
to
permit, I
go?
will give the answer for her
Yeah,
question.
sure, sir, sure, please. Please go ahead,
Actually,
sir.
in Python programming nowadays, just similar to the built-in API support for many of the machine learning techniques.
Yes, sir.
The quantum computing techniques is circuit design and giving the simulated results, which are promising in order to compare the results which have been already proved.
Yes,
But
sir.
here it is completely simulator on a digital computer,
Classical system.
classical computer. It
Okay.
is not a pure quantum computer. What Madam explained, it is pure quantum computer, but you can simulate the same concept using quantum computer simulation can be done. So that is how the theory is going on. I hope AI and ML algorithms will go into change in coming days.
Okay, sir. Okay. Okay, sir. Thank you. Thank you very much.
We move from classical to hybrid, hybrid to quantum. So hybrid is the step which is connecting both the sides.
Ma'am, is that in years to go, is the classic computers becomes absolute in context with this quantum computer?
See, when you have a speed, madam, earlier we never thought of laptops.
That's
Today,
right.
laptops are replacing our classical desktops. A
Yes,
day
ma'am.
will come when the technology, as we move, things will change definitely. Desktops, we may have desktop, because some companies are also having quantum desktops today. That's why I told you, days to come, we may drink quantum computer, we may eat quantum computer. We
Yeah.
ourselves become quantum computers. Hypothetical, but a day will come.
Okay, ma'am. Thank you. Thank you very much.
What is the scope of using quantum computation in image processing?
Sir, anybody can answer, sir. I have resource persons here, I think, image processing, because I am not a specialist in that.
Okay.
Image, again, image classification, image segmentation, all the image storage, huge data is required. So that's all I can say. Whenever you are able to perform transformation on an image, that is computer graphics I talked about, you will be able to perform the storage. And see, parallel operations are the only plus point in quantum systems. That means superposition. When a system goes into superposition, enormous amount of computing power comes up. You are able to analyze your image. A single click, single instruction can perform all operations in parallel on all your segments together. All your pixels can be operated together. A single click can do all bits can be transformed together. That is parallel nature of your system. Very complicated image can be very comfortably analyzed.
Okay. Thank
But
you,
I am
ma'am.
not an authority on image processing.
I think for his question, the answer is till today, when you take a binary pixel, it will be in 0 or 1 state. We never think between 0 and is there any possible states. 1 qubit, when you are able to give enormous number of states are possible between 0 and 1, even a pixel value can take it. In the sense, now we are simulating in computer graphics the same concept. It's more number of bits to be understood with a color graphics support, 8 plus 8 plus plus RGB. Now a single qubit can do this type of simulation in the coming future. That is how image processing will be, concept will be differently visualized, because each pixel is having the support of representing varieties of things in the nature.
That's what. It is possibility of representation. It is 2 power n. That is different values can be operated at the same time. One single qubit can do multiple things. Can change everything. Yes, correct. Sir. Coloring is a problem. I think you know it's a hard problem. Working on colors, graph coloring.
Thank you, ma'am, for answering all questions.
Yeah, thank you. Thank you so much.
Uh,
I don't
for-
know whether I was helpful in
No, ma'am, it was
giving a
given very
no. My
consistently
talk
well.
was only confined to concepts.
Yeah,
Okay,
ma'am.
because I went through the brochure, it had many experts, many resource person in deep they are going to go. So only confined to concepts I've just taught about. And if I am wrong again, I please pardon me. If I am wrong in any part, please do pardon me. And I thank Muhammad Rafi sir and Kavita madam for giving me this opportunity, because over long years I've been working on this, and very happy to share whatever little I know I have shared with you. And thank you all the participants for patiently hearing me, and hope you will have the rest of the sessions very fruitful. And the end of 6 days, you will definitely see a light, a tunnel, quantum tunnel, and a light at the end. Thank you.
I request Nagratna madam to give feedback, or any other participants who are interested. You can just unmute your mic and please share your feedback about this session.
Hello, thank you, ma'am. Your valuable time to spending for this quantum computing. This FDP program to gaining our knowledge and new things. We can improve our knowledge. Also, learning new concept about the quantum computing. Difference between the quantum computing and classical bit and qubit also. Where we have to using that this quantum computing. For example, you are sharing your emerging areas, encryption technology, communication technology, and molecular simulator, where we have to using, how we are to using and all. Thank you so much, ma'am, this FTP program to giving this opportunity to sharing your knowledge. Thank you so much.
Any other participants who want to share your feedback? Sumati ji, ma'am.
Yeah. Dr. Vidyaraj, madam, yours was a very good lecture. I felt it was key takeaways from this 6 days FDP towards the end. I felt all the PPTs and your lecture it concluded all the key takeaways, all the points, like the topics, what we are going to have the discussion within this all 6 days. That was, and towards the end also, it was a wonderful end. And it says, I felt like this is going to be the end session that is going to give the conclusion and the key takeaways of all these sessions. And it was not the end. It is the beginning of a new era for the 6-day session. I felt like that. Thank you very much for the informative session. And I request the coordinators to share the PPTs of this session. It will be very much useful for us. Thank you so much. Thank you.
Thank you.
Yes, ma'am. Everything will be shared. The video link, PPTs. At the end, everyone will get all the resources. Any other participants who want to share the feedback?
Yes, ma'am. I would like to say thank you for this session. It was, I have attended one or two more FDPs on this, but ma'am explained all the concepts very well. It was very nice to get some mathematical idea about quantum, and I'm actually also actively working in this area. So it was a good, introductory session to get an idea about things. And I also believe that vision you have might come true in a couple of decades, where we will all turn into quantum computers. So when you said that, it really hit, that's what I kept thinking. This is what is left now. So, but it was really great. Thank you so much, ma'am, for the introductory. It set a good pace for the forthcoming session. So then when the experts talk in detail, we will know where the basics are. So that was very, very good. Thank you so much, ma'am.
Thank you.
Thank you, ma'am. Any other participants? Shall I conclude? Okay, ma'am. Thank you, ma'am. Vidya, ma'am. It was really like in the beginning you said that I'm just a simple teacher. Like it really suits your words. Like in a consistency phase, the way you explained and you have given the, like other ma'am said that you have given the outline of the entire thing, like bits, even though it was a bit by bit, but still we got the knowledge. What are the different topics we can focus on? How we can learn, like section by section. Even I was very impressed by your way of explanation, the topics you collected, the PPTs, the phase of teaching, the speed, the acceleration, everything was really, really awesome, ma'am. Thank you. It's an honor for us to have you in this session. Looking forward more from you, ma'am. Visit Davangere and to our college also. We shall have some face-to-face sessions as well for our students. It's a great time, madam. Thank you for spending such a
Yeah.
precious time with us. Thank you, ma'am.
Thank you. Thank you so much. Thank you.
Participants, let's take a 10 minutes break. We can assemble at 8:15 again for the next session. Thank you, one and all.
Madam, have you taken a snapshot?
Yes,
Oh.
ma'am. I have taken.
Okay, thank you. Because for record purpose,
Yeah,
thank you.
Yeah,
we
I
need
have
that.
taken. I have taken.
Thank you. Thank you, one and all.
Thank you.
Thank you, ma'am. Thank you.